we present goal-aware prediction, learning to model what matters. Deep model-based reinforcement learning has shown promise in a number of settings, ranging from challenging robotic control to learning directly from pixels. These methods exhibit numerous favorable properties, including sample efficiency, stability, and interpretability. However, scaling these methods to diverse visual scenes poses numerous challenges, the primary of which is underfitting, even with very large models. In these settings, the learned model cannot perfectly model the scene. As a result, learning algorithms must balance how best to learn the model to achieve good performance on downstream tasks. Specifically, in many cases there exists an objective mismatch, where better performance fitting the model does not directly translate to better performance using planning in the downstream task. Motivated by this challenge of objective mismatch, we ask the question, by conditioning the model on the goal, can we focus the model capacity on the task-relevant quantities, enabling better performance on downstream tasks? We assume the self-supervised setting, where we do not have access to any task-specific rewards at train time. At test time, the aim is to plan using the learned model to reach unseen goals. To this end, we propose goal-aware prediction, or GAP. GAP encodes the current observation and goal into a latent space. GAP then reconstructs the difference between the current state and the goal from the latent encoding, while simultaneously forward dynamics are learned in the latent space. Critically, since we're in the self-supervised setting, we don't have access to true goals. Instead, we leverage hindsight relabeling to acquire goal-reaching trajectories. The benefits of GAP are twofold. First, the objective encourages only capturing the parts of the scene relevant to the task, allowing the model to more effectively use its capacity. Second, GAP biases the model towards higher accuracy near the goal, particularly in multi-stage tasks. As the agent gets closer to the goal, the total information about the scene that the latent space needs to capture is reduced. Furthermore, we show in the paper that for sampling-based planning, model accuracy near the goal is most closely tied with selecting the optimal action sequence, and as a result, downstream task performance. In our experiments, we examined three primary questions. First, how does GAP redistribute model prediction error? Second, does using GAP lead to better downstream performance on visual control tasks? And lastly, does GAP scale to real cluttered visual scenes? First, we examine how GAP redistributes model error. We do so by sampling 1,000 random trajectories for an unseen task and ranking them by their true task cost. We then measure model prediction error over the prediction horizon, averaged across the top k trajectories, where smaller values of k indicate better trajectories. We observe that on the best trajectories, or the ones with lowest true cost, GAP in blue has prediction error that is significantly lower than the baselines, which include a standard lane dynamics model in purple, a standard lane dynamics model which predicts residuals from the current state, termed residual model in green, a method which conditions on the goal but keeps the learning objective unchanged, termed GCP, in red, and a method which also conditions on the goal and upweights the prediction loss on states closer to the goal as measured by pixel distance, termed gap weighted, in orange. Next, we examine if GAP improves downstream task performance on unseen tasks in a simulated manipulation domain. In the 4 tasks, the agent must either push 1 block to the target position, push 2 blocks to their respective target positions, or open or close a door with distractors on the table. All tasks are specified by a goal image. We compare to the standard and goal conditioned model-based techniques described in the last slide, as well as 2 additional baselines. First, action reconstruction, which uses an inverse model loss to learn the lane space, and reinforcement learning with imagined goals, or RIG, a self-supervised model-free RL technique. GAP is the top performing method in 3 out of 4 tasks. In particular, in the more challenging 2-block pushing task, GAP significantly outperforms the baselines. Lastly, we compare the distribution of model errors of GAP to baselines on the more challenging data from the RoboNet dataset. We observe that the trend holds, and that for goal-reaching trajectories, GAP maintains lower model prediction error and generalizes to unseen trajectories more effectively. The key takeaways are, objective mismatch is a particularly important problem in vision-based domains. Our goal-aware prediction framework helps mitigate objective mismatch by improving model accuracy on task-relevant states, and using GAP leads to improved downstream task performance.